Okay, so last time we were talking about the equations of motion for the perturbations about the steady state for Rayleigh-Bénard convection. And so we worked out the steady state equations, which just describe a heat conduction. And then we worked out the equation of motion for the perturbations, which I denoted by rho 1 for all the various fields, the density field, the velocity field, the temperature field, pressure, and so on. And then what we did was we looked at the general framework for how we analyze this. And so what we're looking for is we're looking for a perturbation of the system that has a growth rate that goes as omega e to the omega t, and as a perturbation with a wave number k. We've done a Fourier transform, and then we look at what happens to the dispersion relation omega as a function of k as we change a control parameter in the problem. In this particular case, we know that the control parameter is likely to be the temperature difference between the hot and the cold plates. And we saw that there are different cases that I've shown over here on the right-hand panel. One case where the omega has a negative real part, the other where it is marginal, where it just touches the axis, and then the case where the real part of omega is positive within a band of wave vectors k1 to k2. And if the band of k vectors is not too large, compared with the critical value kc, then we can make an approximation such as a one mode or two mode approximation, which is one of the best ways to try to do analytical work on this sort of problem. So that's the stability analysis. And if we want to predict what the scale of the pattern is, we know that the pattern is going to be restabilized by nonlinearities, but we can already guess that the scale at which it is restabilized is going to be determined by the wavelength of the fastest growing mode. That's omega k max on the right and left hand panels there. And so that is our first approximation, at least in the weakly nonlinear regime, for the wave vector of the pattern that forms. So then what we started to do was to try to solve these governing equations. So I'm going to go back and show you how to do that with a bit more detail than I did in the last 5 minutes or so of last lecture. And then we will look at the phase diagram and what's called a neutral stability curve. We'll talk about the types of stability, the general types of instability that the system, the patterns can be unstable to. And I'll show you at the end, if we have time, about the weakly nonlinear theory. So let's get started with our equations of motion. So here on the left are our equations of motion, and I want to focus just on the velocity for now. So put your eyes on the right-hand panel, and let's just look at the top equation. So here are the dirty tricks that we're going to use to simplify this. So we're going to beat this set of equations down into an equation for one variable. And the reason that we can do this is by clever use of vector identities, plus the fact that we've got two equations, one for the velocity field, and that equation for the velocity field then feeds into the equation for the temperature field, because the temperature is advectored by the velocity. So what we're going to do is actually combine the two equations together. So here's how we do it. If we take the first, the top equation, so this is just the equation up here. That's our equation of motion. The acceleration, we've linearized this, so there's no advection term. There's the linear terms. Then what we do is we take the curl of it. Okay, why do we take the curl of it? So we take the curl of it, and I can already see a misprint here. Let me just check that I've got this correct. Oh yeah, no, this is all correct. We take everything I've written down here is correct. We take the curl, and so what happens is the curl goes all the way through. Why do we take a curl? Well, the curl is a good trick to get rid of the pressure. Okay, whenever you're doing fluid mechanics, the pressure is the thing that you hate. Okay, because you have to solve for that. So you can get rid of it just by taking the curl, because the pressure only comes in as a gradient. So you take the curl, and then of course all of these derivatives commute. So then what you end up with on the left-hand side is the diffusion operator, d by dt minus nu del squared, curl u1, and then is what happens when I take the curl acting on the right hand side. Now, the variable nu here is the viscosity, shear viscosity, divided by the mean density. So this thing here is called the kinematic viscosity. And what I've done in taking the curl is I've used the fact that rho 1 is proportional to T1 and rho naught is just a rho bar. So that's fine. So that's an equation in terms of the vorticity. So now what we do is we take another curl. Okay, and why do we do that? Well, you'll all remember the tensor identity epsilon ijk epsilon ilm equals delta jl delta km minus delta jm delta I delta lk. Okay, there used to be a society in Cambridge called the Tensor Society, which had a T-shirt with that tensor identity on it, and it was a great T-shirt to wear to mathematics exams, because it had the identity on it. Okay, but it had the identity on it wrong. So anybody who was trying to cheat would look at your T-shirt and say, that's what I need to do, and then get the wrong answer. Okay, so now we use that identity, and why do we do this? Well, notice that in this identity, one of the terms is this grad div A. I've written it out in vector terms here rather than tensor terms. And why do we care about div A? Well, we've got u as the variable, so div u is 0. That's incompressibility. So we know that once we do this, we actually get rid of one of the terms. So once we've done this, once we now operate on this with another curl, then our equation now becomes the one in pink in the middle of the page. D by dt minus nu del squared, acting on now just del squared u1 from the vector identity, and then you have what's left on the right-hand side, and now you have d by dt, you have del squared t1 on the right-hand side, and another term with involving g. Okay, now remember G is just pointing downwards. So then what happens is the only component of this that's really interesting is the Z component. And the Z component then reads d by dt minus nu del squared W1. W1 is the Z component of the velocity field. And if you look at what's happening on the right-hand side and write out all the terms, what you will see is that you have a minus d2 T1 by dz squared, which conveniently cancels this one that comes from the del squared. And so what that means is that this whole term on the left-hand side is equal to the transverse derivative. I'll call this the transverse derivative. Meaning just in the xy plane. So remember, Z is the direction going up. So if we were looking down on the convection from above, we'd be looking in the xy plane. And so now we want to look at the xy plane because that's actually where we see the patterns. So we've now got the equation of W1 in terms of T, but we don't know what the equation for T is. And the thing is, W1 is in terms of T, but we know that T is advected by the velocity field. So you can think of this as like in general relativity, where space tells matter how to move and matter tells space how to curve. So here the velocity tells the temperature how to move, and then temperature tells the velocity how to move as well. The velocity, yeah, let's do it right. The velocity tells the temperature how hot to be, and the temperature tells the velocity how fast to move. And so you have a pair of coupled nonlinear differential equations. That's all general relativity is. Okay, so now what we do is how do we deal with this? Well, now on the left-hand side here, you can see we have this transverse derivative, transverse Laplacian of T1. So we say, okay, fine. Well, we know that the temperature field obeys the diffusion equation. So now we take this whole equation and now operate on it again with a diffusion operator, but this time it's the diffusion operator for the diffusion equation. So here I'm operating on it with this operator. This has got kappa in it, the thermal diffusivity, whereas this one over here is the del square that comes from the Navier-Stokes equations and has the kinematic viscosity in it. So now we end up, after I've done all that, now I've got this very beautiful equation right here in the middle, which is a single equation that just involves W1, the Z component of the velocity. So that's the sequence of tricks that I used to get this. Actually, I didn't do this first. The first person who did this was Lord Rayleigh about 120 years ago. Okay, so now we solve this by separation of variables. So we solve it by separation of variables by writing W1 as a function of Z. That's in the direction where the heat is moving. And then in the transverse plane where we see the patterns, X, Y. And then as usual, we expect there to be a perturbation growth rate. So that's going to go as e to the omega t. And so now when we do this, we have to solve this by separation of variables. So the only way that I can have a function of x and y equal to a function of z and t is if they're all a constant. And so I end up with a constant which is a, that's an eigenvalue. And we end up with the equation which I've written down at the bottom of the page, where I've written down the vector, the operator d by dz as a d, just to make the thing all clearer. So we have a very we have a very nice differential equation. It's a linear differential equation. It's sixth order, and now we need to solve that. So let's see how do we solve that. So the first thing that we need to ask is, what are the boundary conditions? So let's discuss the boundary conditions. So the boundary conditions that we have are generally what the usual strategy is in perturbation theory is have all the boundary conditions satisfied by the zeroth order solutions, and then the perturbations can vanish at the boundaries. So that's what we're going to do here. So we're going to require that the perturbations vanish at the boundaries. So let me write down what those are. So that says that U1 equals V1 is equal to W1 is equal to T1. Those are the parameters, those are the fields. Those are 0 at Z equals 0 and Z equals D. That's the lower and the top plates. So then what that means is that the derivatives du1 by dx and dv1 by dy are equal to 0. And so that means that dw1 by dz is equal to 0. And that's going to be true at z equals 0 and z equals d. And where all this comes from is because I've got div u1 is equal to 0. So that's the boundary conditions for the velocity. Now we also need to have boundary conditions for the temperature. So we know that T1 is going to equal to 0 at z equals 0 and d, and so now what we do is we substitute that into the equation of motion, and what you end up with is this: the nu d squared minus a squared minus w times the operator d squared minus a squared acting on w is equal to 0 at z equals 0 and d. And so then what does that mean? Well, I can expand that out, and I know that w and dw are equal to 0 at z equals 0 and z equals d. And so then I get this weird boundary condition that says d4w minus 2a squared plus omega over nu d squared w is equal to 0 at z equals 0 and z equals d. Okay, so that is a set of boundary conditions that we need for these equations. They're horrible. Okay, they're absolutely disgusting, but we need all these boundary conditions because we've got a sixth order differential equation. So we need to satisfy we need a whole bunch of equations to be able to solve it. So what do you do when you have such a disgusting equation? So, well, you go and look at the greats. So what did Lord Rayleigh do? Lord Rayleigh said, well, that's too hard to solve. I don't care about that. I'm going to invent my own boundary conditions. So Lord Rayleigh said, let's simplify this to make a caricature problem. So this is too hard. Although, of course, if you were doing this on the computer, you could just do it. So what Rayleigh did was to simplify the problem. Today we would say you'd make a toy model. This is a toy model of a toy model, I suppose. So what we'll do, we'll simplify the problem to make a caricature. And so he said, let's do this. Why don't we just say that W is equal to D squared W equals D fourth W, and those are equal to 0 at Z equals 0 and Z equals D. So those are much simpler, and they're clearly related to what we have. It's still pretty hard to solve, but at least we can make some progress. So we're just going to use these boundary conditions. And what are we going to predict? What we're going to try to predict is when the real part of the growth rate changes sign, going from negative to positive. So once we can predict that, then we've actually predicted how hot the temperature needs to be, how big the temperature difference needs to be in order to have convection. And that's the calculation we're going to do. So let me just show you very quickly how we do that. So the first thing is you can see it's pretty obvious that W of Z in the Z direction is just going to be sine pi n Z n pi Z over D for n is equal to 1, 2, and so on. So that's going to be the boundary condition that satisfies the behavior in the Z direction. So and then if this is going to be the behavior, then we now have the governing equation to then determine. So what we're going to get for the governing equation, I'm going to just write the solution down, is the following. Let me make sure I copy it down right. So if this is going to be true, this will satisfy this is a solution of the governing equation and the boundary conditions. So we can say by inspection, but you could do it more formally if you wanted. And this gives you a condition, and that condition is the following. So I'm going to write it down: omega plus nu A star squared, omega plus kappa A star squared, plus alpha G d T naught by dz A squared is equal to 0. So that's an algebraic equation, and I would define a new quantity. So I call this quantity A star squared. It's another eigenvalue. This is A squared plus n squared pi squared over d squared. And now I plug that into here, and I've got a quadratic equation. So now I can solve for W, solve for omega. So let me just write down what the solution is. It's a horrible mess, and you're not going to follow this in real time. But if you want to afterwards, go ahead and try it. So what you get is this nu plus kappa A star squared plus or minus, and then 1/2 nu plus kappa A star squared to the 4th plus, this term is really important, alpha G delta t over d a squared over a star squared minus nu kappa a to the fourth, and then just that, and then all of this to the 1/2 power. Okay, so this all seems really obscure. You've just got these eigenvalues that you have to compute. They have certain values. They are, you just plugged into this equation. So now let's just simply plot these eigenvalues. So let me show you what it looks like. So think of it this way. We have three wave vectors. Well, really two, I suppose you could say. So we have a wave vector in the z direction, that's k, which is n pi over d, and then we have a in the horizontal direction, in the xy direction, and that has values that are determined, are related to the ones by n, and so let me plot for you what they look like, and then I'll explain to you where they come from. So here is our axes. So this is going to be, I'm going to plot here a d. So a is like a wave vector. Here I'm plotting omega. This is 0, and I'm going to define a particular number, which I'll call r. I'll define it in a minute. Let me show you what this curve looks like. So it looks like this. So the curve looks something like this. This is, I'm just going to label them and I'll tell you what the R means. This is R is 0.5 RC, and this one is R equals 1.5 RC, and this point here is about 1, 2, 3, 4, something like that. And there's two numbers which I'm going to tell you what they are. So I'm going to just write this down. This ratio is nu over kappa, and this is equal to 1. Okay, so if you solve this equation, you will end up with a dispersion relation which does indeed change sign as you vary a parameter, and I want to tell you what that parameter is. So the parameter that we have here is so let me go to these notes. Okay, so the first parameter is the Prandtl number, which is nu over kappa, and the second number is the Rayleigh number, and that Rayleigh number is defined as follows: alpha g delta t d cubed over nu kappa. So this is Prandtl number, and this is Rayleigh number. Sometimes people call it, write it as RA. And if you want to work out what is the critical Rayleigh number, the critical Rayleigh number, you can read it off. You can do, well, you have to calculate it. The critical Rayleigh number is about 1700 when nu over kappa is equal to 1. So what is the significance of these numbers? So let me show you. So let me make some comments then. So the first comment I want to make is about the Boussinesq approximation. And I'm going to tell you where these numbers come in. So there's a Boussinesq approximation. I don't know if I spelled Boussinesq right. So there's two ways that the density comes into these equations. The density comes in, first of all, as the inertial term, multiplying the du by dt plus u dot grad u. But then it also comes in the buoyancy term. So what we've done in this case is we've neglected the temperature dependence of the rho in the inertial term. So we have a term that looks like this: rho d by dt plus u dot grad u equals blah blah blah. And so in this term here, rho should be the regular rho plus the rho that gets from the thermal expansion. So what we've done here is we've neglected the thermal expansion. But we've included it on the right-hand side where we have the term that multiplies the gravitational field. So that's called the Boussinesq approximation, and it's a reasonably good approximation. Then the next thing that we've done is so the next thing that you can do is you can non-dimensionalize these equations. Now, I'm not going to write down. Actually, am I going to write them down? Let me just see if I believe the equations are in my notes here. Yeah, I don't believe it. I don't believe these equations. But anyway, I'm going to. You can non-dimensionalize this. So you can redefine units of time, space, velocity, temperature, pressure. And when you do that, these are the following definitions. So you make a new time variable, which is d squared over kappa times t bar. A new space variable, which is x, is d times x bar. So all the barred quantities are the redefined units, dimensionless units. A u is equal to kappa over d u nu u. T is equal to nu kappa over rho d, that should be rho g alpha d cubed t bar, and the new pressure is rho bar nu kappa over d squared, and then the dimensionless pressure. So all of these are dimensionless variables. And once you put it in those forms, the equations then become much simpler. That all of the alphas and g's and everything drop out of the equations. And there is a version of this in my notes here, but I don't believe it. I think when they were written down, they're written down wrong. So I'm not going to put them on the screen. So so let's leave it like that. And so that gives the equations of motion in a non-dimensionless form. And I don't remember them accurately enough to write them down and get them right for you. But in the end, the equations just have two numbers in them: the Prandtl number and the Rayleigh number, and everything else is dimensionless. So just a two parameter family of differential equations describe all convection phenomena. What happens in miso soup? What happens on the surface of the sun? All described by more or less the same equations. Okay, so that's basically the solution of the problem. There's a critical Rayleigh number which is 1700. It's not. You can make a more accurate number for it, and you can do the same thing for other instabilities in fluid mechanics and so on. So the basic idea is this is the thing that we regard as the solution. This predicts the phase diagram. So what we've done over here then is we can say that our phase diagram is in terms of the Rayleigh number. So here is 1700. Here is 0, and then here it is at rest. Here it is starting to move. You're getting convection, and then there's more transitions as you go in this direction. So as you increase the Rayleigh number, you make the plate spacing bigger, or you make the temperature difference higher. You get more transitions, and eventually you get transitions to turbulence. So I have friends who do experiments with Rayleigh number of 10 to the 14. And they look at the scaling laws and they try to work out how does the heat transport scale with the Rayleigh number. And you would think you can go over 14 orders of magnitude. You would think that you'd be able to measure an exponent over 14 orders of magnitude. Okay, people argue about what the exponents are for what happens for highly turbulent convection. It's astounding that even though you can do experiments with 6 or 8 decades of scaling, you still can't. People are still unsure if they can read off the power law correctly. So if you can't do it for 8 decades, then whenever you see somebody else in any other field like biology or condensed matter physics telling you a power law and they've got maybe 1 or 2 decades, you should treat it with a grain of salt. The worst example of a scaling law that I know of is a scaling law in biology called the Kleiber's law, or the metabolic scaling law. That tells you the basal metabolic rate of an organism as a function of its mass. This scaling law works from blue whales and elephants all the way down to bacteria. Okay, so it scans about 22 orders of magnitude, and you would expect, if I asked you make a 5-second theory, or even 10-second, a 5-second theory for how the basal metabolic rate scales with the mass of the organism, you would mutter something about surface to volume ratios, and you would say the exponent should be 2/3. Okay, but it's not. It's 3/4. Okay, and then of course some people say no, it really is 2/3. And so it's very difficult to read off exponents from graphs, which is why all those people who know me well, work with me, know that I don't like plotting power laws. I like plotting universal scaling functions. Okay, so let's now talk about a little bit more about what we've learned and discuss a little bit more about what happens as we go through this transition. So this is just the very first transition, okay, from a uniform state to a state with a pattern, okay? All the other states at higher Rayleigh numbers, they all have patterns. So everything that I just did now becomes much more complicated if you want to go to higher Rayleigh number. So let's let's talk about how we go to higher Rayleigh number. So the next question. After we discover the instability to convection, what actually is the behavior? So remember last time we said that we don't really know the answer to that. We can't answer it by linear theory, because remember, when things become unstable, they get restabilized by the nonlinearities. So we've neglected the nonlinearities so far. So even though this was quite a complicated calculation, which I simplified for you, it's still absolutely trivial compared to what we actually need to do. So now let's talk about, so after we discover what actually is the behavior, so that for that we would need to understand nonlinearities and construct candidate states of the system. So let me tell you what I mean by that. So what I'm going to do is now in section 7.5 of my lecture notes. This is the if you like, the qualitative picture of the phase diagram. So what is the basic idea? So we're going to say that we're going to talk about a thing called the neutral stability idea, neutral stability curve. So what we're going to say is this. I look at the real part of the dispersion relation, omega of Q, but omega of Q also depends on the Rayleigh number. And so if that is equal to 0, and that is the line in the Q and Rayleigh number plane, which defines where the system is stable or unstable. So this demarcates a boundary between stability and instability. And as we already talked about, we're looking at the dispersion relation. So modes that are stable in some wavelength of Q may be unstable in another range. So the graph that we plot to characterize this looks like this. So I plot over here wave number of the instability. And up here, I plot the Rayleigh number. And this is now Rayleigh number for a different Q. And there's a critical value that we just calculated, or Rayleigh calculated, which is over here. So below this line, the fluid is stationary. So uniform fluid at rest is stable. And then then we know that that line has, when you go past the control parameter, there's a Q value where it becomes unstable. So here's the Q value that it becomes unstable at, if that's over there. So now if I translate it into this kind of curve, what I end up with is a curve that looks like this. So something like that. So anything above here is unstable. And we want to find out what happens. So this is the value Rayleigh C. So now we want to know what happens above that. So the only way to proceed, we don't have any variational principles or in general any other way to calculate. So what we do is basically guess. We guess solutions based on their symmetry, and then we look at what their stability is. So we're going to say, okay, we found a uniform solution that was stable for some values of the Rayleigh number. Maybe there's going to be periodic solutions. So what we do is literally guess solutions. I mean, they're educated guesses. So we're going to guess solutions and see if and when they are stable. So let's have a look at one of these solutions. So you might say, well, I'm going to guess that we're going to have stripes. So what would a stripe look like? Well, the picture, if I looked at it from above, might look something like this, where you've got some stripes oriented along the y-axis, and so this configuration would look like this: u of z is equal to some amplitude times some function uq of z, and then e to the I q naught x plus the complex conjugate. So that would be stripes in the xy plane, and then in the z direction, some other function u of z associated with the wave number q. So that would be how you could write down stripes. Another thing that you might guess is you could say, well, there could be squares. So the way you would write this is you would say, well, u as a function of x is equal to some magnitude, some field in the z direction, and then e to the I qx in the x direction plus e to the I qy in the y direction plus complex conjugate. So that would be another kind of solution, something which is like square or rectangular, something like that. So and you can try to construct many other things. You might do hexagons, whatever. So now the question is, are these any of these states, are they observed? And not only are they observed, but if they are, in what range of parameters? Because some of these states may be observed in some range of parameters, but not in others. So in what range of, say, Rayleigh and Prandtl, for example. So the answer to that is we don't know which are going to be observed, but we know that if they're unstable, they're definitely not going to be observed. So what you do then is you now do linear stability analysis. Of these states. So now that's going to be very, very complicated. So when we do this, the linear stability of these states, that's called looking for secondary instabilities. Why are they secondary instabilities? Well, the first instability was that the uniform state, the stationary state, broke up into some other state with a pattern, which we're going to have to figure out what it is. And then now we're looking at whether the pattern breaks up. But the pattern is already periodic. So when I look at perturbations about the periodic pattern, what I'm actually doing is flow-K analysis. I'm doing flow-K analysis because I'm now looking at the stability of a differential equation, but the differential equation is not about a uniform state, but a state that is periodic. So it's like having the Schrödinger equation in a periodic potential. So I'm doing basically band structure analysis for these patterns. So that's what I'm going to talk about now. So the base state is the state uq, which is some function of x, y, and z, and so this is the state that is the pattern periodicity. Okay, so that's the problem. So now let's talk about how we examine. Now let's talk about how we examine the stability of these non-trivial states. So now we're going to have a perturbation about a periodic pattern state. So I'm going to write that perturbation as delta U, and I'm going to write it in the following way. It's some U1 of x transverse x in the x and y direction, then in the z direction, then it's going to go as e to the I q dot x in the transverse direction, and then e to the omega t. And when I mean x transverse is equal to x, y. Okay, so that's how I write down the perturbation. So then you might say, well, okay, so what is this omega? Well, this omega here, you might say, oh, this omega just depends on q, just like we did before. Omega is a function of q, but it's not, because it also depends on the base state that you're perturbing around. So the complication is that omega is equal to omega is indeed, it depends on the perturbation q, but it also depends on the pattern q, like so. And that's why this becomes complicated. So of course, I'm not going to tell you how we do the calculation. Very, very technical, and we could, I mean, it's interesting and so on, but you know, if you go to a fluid mechanics class, maybe they describe it. So I'm just going to show you what the result looks like. So let's look at the outcome. So I'm going to plot up here. Here I'm plotting the Rayleigh number. And then here I'm plotting Q, the pattern. And then I'm going to draw here the critical Rayleigh number, where things start to happen. And then I'm going to draw the neutral stability curve. So I sort of sketched the neutral stability curve for you before. So it does something like that, comes down with some wave number and touches this curve at the critical wave number. So this is the neutral stability curve. Okay, so now when you look at this curve, what you're supposed to say is, in this region here, in this whole region, a periodic pattern well, in here, a uniform pattern, i.e. no pattern at all, is stable. In the above this neutral stability curve, it might be that a periodic pattern is stable, or it might be unstable. It turns out that there's another region in this curve, which looks like this. Right, yep. So in this region here, this region, the periodic pattern is stable. And so in this region over here, the periodic pattern is unstable in this region and in this one over here. So I'll do the same thing here. So this, so we don't know if we don't know that the pattern is going to be stable or not. You have to do the calculation, but you know it's a solution. So just because you found a solution of the equations doesn't mean it's going to be observed. You have to see if it's going to be stable. So this region inside here, this has a name. Some of you may have heard it before. This is called a Busse balloon. Why? Because the first person who did these sorts of calculations was Fritz Busse. And these are really complicated calculations. Okay, you have to do a lot of work to do these things. But I want to show you just two things about these patterns. So the question that we might want to ask ourselves, an interesting question, is how does the periodic pattern go unstable? So I want to what I want to show you is that there's different ways these patterns can go unstable. So let me answer that as follows. So this on the left side of the Busse balloon, the instability. So the left side, that's here, the left side, the left one that you can see, that goes unstable through a thing called the zigzag instability. And I'm going to draw a picture of it in a minute. And on the right-hand side, it goes unstable through a different instability known as the Eckhouse instability. After the person who first identified it. And let me show you a sort of cartoon picture of what these things look like. So in the zigzag instability, so what we're looking at are periodic rolls in the x direction. So that was the first, the striped phase, if you like. So that's the one I've shown you over here. And so the zigzag instability is that the rolls become like this. Okay, so they literally become a kind of zigzag pattern. I don't have a picture to show you. I'm not going to go and look for a movie of it. So you'll have to just take a sketch. And then what the Eckhouse instability looks like. So this is an instability where the rolls change locally their wavelength. So that would look like something like this. So something like that. So that's a change in the period. Okay, let me just go back to my lecture notes. Seriously? Okay, so let me okay, so let me just try to show you a little bit about what these things look like. So I'm just going to just show you about the one-dimensional stripe patterns. So we can look in the first Brill one zone. So then I've got minus q over 2 is less than qx is less than q over 2. And so now you can ask, so this is the wave vector of the perturbation. So how can it go unstable? So there's many possibilities for instabilities. So I've just shown you several, 2 of them. But let me tell you about some of the other ones. So you could have, for example, that q is actually equal to 0. You could have that q is on the zone boundary. You could have that the magnitude of q is much less than the magnitude of the pattern wave number. And so this is a long wavelength instability, like the Eckhouse instability. And you could have q, I don't know how to say it, I'll just write it. Q is incommensurate with little q. So in other words, the wave vectors for the instability and the wave vector for the pattern have different periodicity. So all of this, people spent, I don't know, 20 years working all this out. There's a famous article in Reviews of Modern Physics. I'll write it down here. Cross and Hohenberg. Rev Mod Phys, 1993. That is basically the Bible for everybody who works on pattern information. The classification of all the possible states here is enormous. Pierre Hohenberg loved classifying things. He classified critical dynamics. He loves classifying pattern instabilities. So he's written these famous, long, seminal articles in Reviews of Modern Physics, which, in critical dynamics and then pattern formation, of course, they were fundamental to the field. He just liked doing that. So then let me just finish this part by telling you about what the Eckhouse instability looks like. So example, if I wanted to know what is I talked about zigzag first. So if I want to know what gives you the zigzag instability, so that is where qy is equal to 0. Sorry, actually, that's not true. What I said was completely wrong. Qy is much less than little qx, and qx is equal to 0. So that's the thing that gives rise to the zigzag instability. You can kind of see that because in the x direction there's no change in the periodicity, but in the y direction there is a wiggling. And then if I look at the Eckhouse instability, so for the Eckhouse instability, so qy now is equal to 0, and qx is much less than little qx, and so that gives rise to the pattern I've shown on the left, and you can then work out the dispersion relation. And in one of them, you find there's a parabolic dependence or a linear dependence on the Rayleigh number, depending on which instability you have. So these have different dependencies on Rayleigh minus the critical Rayleigh number. So, okay. So that's all I want to say about linear stability analysis. Yeah, quick question, EJ.
So in the about in the instability diagram, that diagram also depends on the
Does it depend on?
Depend on the web number of
Yes, so you could work out a dispersion relation as a function of Q. So when you do the calculation, and I'm not showing it to you, you calculate the omega, and so you can find out what you can predict what is the likely wavelength of that pattern.
But for all the capital Q, it's only like slightly change the shape of the. I mean, because I think it depends on both Q.
It depends on both Qs. That's correct.
And if we focus on the different Q, it would slightly change the shape of the curve.
I mean, so the pattern that you get is the one I've shown you over here on the left, and then you can work out which pattern is the one you're likely going to see from the dispersion relation, at least within linear stability. Yes, Rita.
So, like if I look at the phase diagram, like I take a finite size that is a cutoff on Q, and I start cranking up the temperature.
So cranking up the what?
Like the temperature difference between these two plates. So initially it'll be uniform, and then it will go unstable, and then stable.
Yes, yeah, exactly. You get very weird sequences of transitions between these different states.
So you need a high enough temperature to see this periodicity.
Yes. But remember, I've only drawn it here for stripes. You may get in the intermediate phase. I don't know if this is true or not. Depending on the boundary conditions and geometry, you may get other patterns in the intermediate phases. So if you look in Krosno-Holmberg's article, it's like 100 pages of reviews of modern physics. So it's like a book. All of these different patterns that you see and what the phase diagram is worked out.
What would be the possibility other than periodic?
Well, you can have hexagons. You can have orthorhombic states. You can have there's nothing to say you have to have just stripes.
But I'm like here we're doing a 1D
Here I'm just looking at a pattern that is periodic in one dimension, just to show you this. But I can do the same thing for squares, for orthorhombic, for tetragonal, for hexagonal, all sorts of different ones. And I can see in some of those parameter ranges where the stripes are not stable, there may be other solutions that are stable.
But it's going to be hexagons, periodic hexagons.
There'll be periodic ones, but they will also have their own instabilities and so on. So it's very different from equilibrium stat mech, where you just find some boring solution. Right? Okay. So now I wanted what I want to move on to now is on the nonlinear theory. Let me just look in my. I'm looking at two different notes here, and I want to make sure that I give you the right one. Let me just follow these ones. All right. And I remember that when you follow these notes, there is a typo in one of these places, and I don't know if these notes have the typo in or not. We'll get to that. Okay, so I want to now look at section 7.6 in my typed notes. Typed notes are worse than my handwritten notes, because there's another set of handwritten notes which the typed notes were made from. Those didn't have any errors, but the typed notes did. And I haven't corrected them in the typed version because I haven't written the book yet. Okay, so let's look at now. What I wanted to show you is a quick and dirty way to do the nonlinear theory for pattern dynamics. So what I've just told you, today and last time was basically take any solution that you can construct and then see if it goes linearly unstable. And that is virtually, I'm sorry to say, it's virtually the only tool we have in pattern formation to study these non-equilibrium systems. But there's one other tool that we have, and so I want to tell you how we go into the nonlinear regime. How do we see how these patterns get really stabilized? So what we're going to do in this section is we're going to approach the problem of restabilization. So most people who write papers on path information, they never go beyond linear theory. It's already so complicated, okay? But we're going to go beyond it. So I'm going to show you, this is a whole topic, which is, if you want to search on Google, bifurcation theory. And what I'm going to show you is what people call the weakly nonlinear theory. So this is the lowest order nonlinear theory, which is normally done by methods in applied mathematics known as amplitude equations. And those amplitude equations turn out to be really bad because they break a lot of the symmetries of the problem. They're not covariant. And in order to work out the amplitude equations, you have to do perturbation theory to a sixth order in perturbation theory, which is usually, at least when I've done it, it's about 120 pages of algebra. And if you make one mistake, then you do this calculation in order to calculate the sign of a cubic term in an expansion. And if you make a mistake and you get the sign wrong, then you'll predict the wrong physical result. And that term, that is the coefficient of that, is the sum of, I don't know, dozens of terms that takes 120 pages of algebra to work out. Okay, so it's a very nasty calculation. So I worked on those things when I was a postdoc, and I thought there should be a better way to do it, and there is. The better way to do it is using the normalization group, which I discovered maybe 10 years later. So I'm going to show you a very, very simplified version of the renormalization group way of trying to do these sorts of calculations. So it's not, I mean, it's a pretty good way to do things, but there's another way based on the renormalization group, and the reference for this would be my own paper starting in that was in 1996. Actually, where is it? Phys E. And amplitude equations. I'm not going to give you a particular reference. There's plenty of good references by people like Alan Newell and others. I can put them in team chat afterwards. This again, just a little bit personal interlude before we get into the mathematics. The RG calculation I'm going to show you. We did this calculation and it was really quite fantastic, but this is where the principle of least action is not your friend. So if you take one of the equations that describes convection and you try to analyze it, and I'll tell you a little bit about it later, it turns out that when you do it by renormalization group, you get 7 divergent terms, and you have to renormalize all of those things using renormalization constants. Okay, and so one of the tricks that people in field theory often do is you say, well, this is way too much work. Let's just look at the most divergent terms. Those are going to be the ones that matter. So that's what we did. We just looked at the most divergent terms, which is only 3 of them, and we worked out the theory and worked out everything. And we derived much less work, the equations that people had done, what I call the Newell-Whitehead-Siegel equations for convection. We worked those things out. Unfortunately, it was a very stupid thing to do because after that, Robert Graham, applied mathematician, theoretical physicist I've forgotten which university he's at in Germany, but he actually realized that we were idiots. So he went and showed it's actually quite easy to do the renormalization theory for all 7 divergences. And when you do that, you get a rotationally covariant form of the equations. So in these stripe pictures, in all these pictures I've shown you, the stripes go up the page. Okay, that's the y direction. So we're doing stability analysis about stripes going up the page. But you may say, well, suppose the stripes are pointing like this, or some other way. Okay, you should have a rotationally covariant description of these perturbations. Okay, so you can do it. But to get that, you have to renormalize all the divergences that appear in the theory, not just look at the leading order divergences. So I missed that. But anyway, so it works pretty well. So we're going to do something very simple. So we're just going to do this in a very simple way. So here, what we're going to do is a quick and dirty calculation. And so that's what we're going to do next. I'm not going to finish it today, probably. So we'll do it, continue next time. So let's suppose I have a dynamical system with 1 degree of freedom. Okay, so it obeys some equation like this: u dot is equal to f of u. But now what I'm going to do is I'm going to put in here some control parameter epsilon that's going to control the behavior of the system. So let's suppose that when epsilon is less than some critical value, that u is equal to 0 is a stable solution. Okay, and then we know that near, let's suppose that that epsilon greater than or equal to some critical value, then now we get a different solution. And so far, I'm just talking about an ODE. We're going to turn it into a PDE later, so that we have some instability. So we're going to follow Landau's idea. Okay, everything we're going to be doing is in the Landau picture. So we're going to say, okay, well, fine. Then let's write f of u as some expansion about u equals 0. So you write it like this, and then I'm going to say, well, in u equals 0 is a solution of u dot equals 0, and so that tells you that the coefficient a must be 0. Okay, so the next thing is that we know that there's going to be some kind of bifurcation at epsilon equals epsilon c, and so that means that we require for the bifurcation at epsilon c, then that means that b must change sign at epsilon equals epsilon c. So otherwise we wouldn't be able to get a non-zero solution. So then what we'll say then is that we can write b as equal to some b naught epsilon minus epsilon c plus higher order terms, like that. And we're going to say that b0, his coefficient, is positive. So that's the first thing. Now let's suppose, it doesn't have to be the case, but let's suppose that we have a symmetry so that the system is symmetric under u goes to minus u. So for example, we might have that u goes to minus u is a symmetry of the governing equation. It doesn't have to be. In convection, for example, you get terms that are, when you write down the order parameter and so on, turns out it's not really symmetric. There can be terms that break that symmetry. And when you break that symmetry, you go from having stripes to having spots, to hexagons and things like that. So knowing the symmetry is a very important determinant for what the pattern is. So let's suppose just for example, that we have such a symmetry, then that would then tell you that C equals 0. And so that means that near the bifurcation point, we have the equation now is u dot is equal to r u plus d u cubed, where I've defined r to be b naught epsilon minus epsilon c, and d, well, d could be either positive or negative depending on the problem. So this is now very much like in the way that we constructed Landau theory in equilibrium. It's exactly the same thing, but now we're doing it for an equation of motion rather than just for a free energy. And do you have any questions, Peter? Okay. So I've put d can be either positive or negative here. We're going to come to what d is in a minute. And actually, this is where I may have a misprint in what I'm going to write down. And since you're all smarter than me, at least collectively, if not individually, and you're further away from the screen, so you'll spot it before I do. So let's have a look at steady states. So I'm going to look at the steady states in the case where I think D is negative. Okay, so you have to check this because I may have got this wrong in my notes. Okay, so then what does the solution look like? So then I can have U is equal to 0 when R is negative, and yeah, I definitely have something messed up here. I think this is D greater than 0. I'm going to just write it down and then we'll see. And then I can have U is 0 or plus or minus R over D to the 1/2 when R is greater than 0. The reason I got confused was I originally defined R to have the opposite sign. So here, as I increase epsilon, I go into the ordered phase, right? So yeah, so R being positive. So then to have the solution, I need D to be positive. So this is definitely not correct. Do you guys agree with me that this should be D greater than 0? Yeah? Yeah. Thanks. Okay, so that's the case when D is greater than 0. If I have D negative, then I can have the following. U would be equal to 0 when R is greater than 0, but U could either be 0 or plus or minus R over minus D to 1/2 when R is what?
If D is positive, it will go to infinity, U is God. So it means D is negative. It's wrong a large displacement to go back to it. So D should be good. Very positive, indeed positive, if you go to infinity.
Wait, don't randomize me. I think I've drawn this the right way around. Well, guess what? We only got 1 minute to go. So I'm going to fix my notes and get it right for you for next time. What I'm trying to draw for you, I didn't hear your question properly, so let me just finish and then so I'm going to fix this next time. So so let me just draw you the final result just for now, and then we'll do this again next time. So what I want to show you is this. The state of the system can either be something like this, and then you either go up like this or like that, or it can be that that actually this thing here, the shape of this, just take us back. Something like that. And so here, what happens is you have a finite jump. And here it is continuous. I'm not going to put on this, which is in which case is D is positive or negative. Okay, and I'll fix it afterwards and make it right next time. So this is discontinuous. This is called discontinuous. This is obviously discontinuous. You're saying, well, this is probably like a first order transition, this is like a second order one. And so that's true. This is called a subcritical transition. This one here is called a supercritical one. So that's the dynamical systems picture, just for 1 degree of freedom. Okay, so we have to finish. So I'll take questions in a minute and outside. So next time we're going to finish this, and I'll show you how to put in space. So let's leave it like that.